This lesson will look at discrete probability distributions. Let's begin by reminding ourselves what discrete and continuous variables are. A discrete random variable typically results from counting, like 0, 1, 2, 3, and so on, while a continuous random variable results from measurement. An example of a continuous number is one's speed at 24 miles per hour. The speed could be anywhere from 23.5 to 24.49999 miles per hour when it's reported as 24 miles per hour. So let's now take a look at discrete probability distributions. The example I have is at Wendy's, a manager performed a study to determine a probability distribution for the number of people, X, waiting in line during lunch. The results were as follows. So X is the variable, and it's a discrete variable. In this table, we can see that there were anywhere from 0 to 12 people in a line. And he tabulated this over a period of time where 0 people occurred 0.011 or 1.1% of the time, and 1 person in line was 3.5% of the time. If we look at this, down below, 4 people being in a line at lunch was the highest probability at 18.6%. One thing that we want to do is verify that this is truly a correct discrete probability distribution. We want to make sure that all the probabilities add to 1. So I took this entire table and pasted it over in Excel. In Excel, I can say right below this column that I want to sum the column of probabilities. And I see that the sum is 1. So yes, I have verified that this is a discrete probability distribution. It says, draw a graph of the probability distribution. Describe the shape of the distribution. So I have already provided this graph, and I obtained it by taking the data from the table and pasting it into StatCrunch. In StatCrunch, I obtained this picture by going to Statistics, Calculators, and Custom. And then I told it that the variable where the discrete variable was at was in the first column, and the probabilities were in the second column. And then I hit Compute. So here I can see that I have a distribution that's fairly symmetric, but it is right-tailed. So I would say that I have a right-tailed graph that is fairly symmetric. The next part of our problem is to calculate the mean and the standard deviation. You'll find in StatCrunch that it automatically gives the mean right below the graph and the standard deviation also immediately below the graph. So going back to the problem, you can see that it says compute and interpret the mean of the random variable X. So if I'm only asked to compute it, I could use technology. If I am asked to do this by hand, then it is a formula that I'll use Excel for in a moment. So for computing and understanding the mean, I'll go back to my graph. The mean had been 4.87. What that means is on average, there were 4.87 people in line at lunch. And we can see that that's about right. The highest point is at 4, though we do have more people on the right side of that. The standard deviation is 2.23, which means if we were to go to the left of our mean, 1 standard deviation to the left or 1 standard deviation to the right, about 68% of our data would fall in that range. The next question is, what is the probability that 8 people are waiting in line for lunch? I can find 8 people in line was about 0.063. So the probability that 8 people were in line for lunch would be 0.063. Last part of this question says, what is the probability that 10 or more people are waiting in line for lunch? 10 or more would be 10, 11, or 12. And so to find the probability that there are 10 or more people in line for lunch, I would add the probability of 10, 11, and 12 together. And when I add those probabilities, I'm going to get 0.029. Last part of this question is, would this be unusual? And yes, it would be unusual to have 10 or more people waiting in line for lunch because the probability is less than 5%. I'm going to shift back to calculating the mean and the standard deviation with Excel at this point. So we can see that the mean is calculated as the sum of every discrete x value multiplied with its probability. And I would do this in Excel instead of having to do this by hand. In Excel, I can paste my two columns, and then I can create a third column and say I want this column to be equal to the x value, the discrete value, multiplied with its probability. Of course, 0 times any probability will be 0. I'm going to drag this formula down, and by dragging it down, it's going to take every discrete value over in the first column and multiply it with its probability. Now I want to find the sum of that column. As a reminder, I can write equals sum, parenthesis, highlight the cells I want to add, and 4.87 is the mean. That mean is the same as what we had found before. For the standard deviation in Excel, I would create one more column. The standard deviation is the square root of the sum of every discrete value squared multiplied with its probability. And once all of these have been multiplied and then the results added, I then subtract the mean squared from it. All right, so let's go back to Excel, and I'm going to take every single discrete value and square it, so multiplying by itself, and then going to multiply by its probability. Drag that sales formula down. I now want to find the sum of that column. All right, so the sum of every x value squared multiplied with its probability is 28.686. Now to get the standard deviation, I need to take the mean and square it. So you can see I created a cell that says mean squared, and to the right of it I'm going to write equals. I'm going to take the mean and I will square it. So here I have the sum of x squared multiplied with its probability, and I have over in this cell the mean squared. I want to subtract those and take the square root of it. And I can, of course, do this arithmetic in a calculator if I wish. The standard deviation is 2.229, which is exactly the same as what StatCrunch had provided. Right, going back to this information, one thing that I also liked about StatCrunch, I thought was pretty clever, is down in this bottom section, it's the probability of x. And then it has some toggles for if it's less than, greater than, or equal to. So if I wanted to know the probability of 10 or more people waiting in line, I would want the probability of x is greater than or equal to 10. And I can hit compute, and it will tell me that it's 0.029, which we had found earlier by adding up the probabilities by hand. If I wanted to know if 9 or more people in line was unique, I could see that it ends up being 0.064. So 9 or more people being in line is not unique or unusual because it's greater than 5%. Well, maybe I want to know if 0 people being in line is unusual. Well, yes, 0 people being in line is unusual as it is 1%. Maybe I want to know if it's less than or equal to 1. So this would be 0 people being in line or 1 person being in line. And yep, that's unusual to have 0 or 1 person in line during the lunch hour. Well, that one example covered a lot of material, and I hope that it helps.